Everyone. Today I am going to walk you through an exciting deep learning project where we build, train, compare two of the most influential neural network architectures in NLP, the long short-term memory and the transformers. We aren't just using an API today, we are building these models entirely from the scratch using the PyTorch. Our specific goal is character level text generation. Unlike large language models like ChatGPT that predicts the next word or token, our model has to learn language at its absolute most fundamental level. That is like predicting the next single character based on the sequence of characters before it. If we feed the model H, E, L, L, it has to figure out the highest probability next character is O. To do this, it has to learn the words, spaces, grammar, punctuations, and structural context starting completely blind. We'll be training this on a tiny Shakespeare dataset so our model learns to speak like Shakespeare. Before we get to the PyTorch code, let's talk about the environment. Reproducibility is crucial in machine learning. So I have fully containerized this project using the Docker. Looking at our Docker compose.yml, we define a single service called app. Notice the volume section. We are mapping our local input, results, models, and SRC directories directly into the container. This means any code changes we make on our host machine instantly updates in the container without needing a full rebuild. We keep the things lightweight. Our requirements.txt primarily relies on TOS, the CPU version, to make this accessible for standard laptops, NumPy and Matplotlib. And to manage our hyperparameters like learning rate, batch size, and epoch counts cleanly inside a .env file so we don't have to hardcode values into our scripts. A neural network cannot read text, it only understands the numbers. The first step of our pipeline is translating a raw Shakespeare text into mathematical tensors. This is what happens in the prepared data.py file. First, we read the entire text and extract all the characters from it, like all the unique characters. This becomes a vocabulary. We then create two mapping dictionaries, cat to int to convert the letters into numbers for training, and into char to convert the model's numerical outputs back into human readable text later. Next is our batching logic. We slice the massive array of integers into smaller overlapping chunks. If a sequence length is 100, the x is characters 0 to 99 and the y is characters of 1 to 100. We yield these as PyTorch tensors so our model can process them efficiently. So let's look at our first architecture, the LSTM. Standard recurrent neural networks struggle with remembering things over a long sequence due to a problem called its vanishing gradient. The LSTM fixes this using a series of gates for get, input, output that will allow it to actively decide what to remember and what to forget. Inside our LSTM model class, which inherits from PyTorch and module, we have three main layers. NN.embedding. This turns our integer character IDs into enhanced mathematical vectors. NN.lstm. The core recurrent layer, it processes the sequence and updates its hidden state. NN.linear. The fully connected output layer. This maps the LSTM complex hidden representation back to the size of our vocabulary, outputting the raw prediction scores for the next character. In the forward pass, we pass the data through the embeddings, the LSTMs, and the final linear layer returning our predictions, and the updated hidden state. Now let's look at the architecture that powers modern LMs, the transformers. Unlike the LSTM, the transformer does not process data sequentially, it processes the entire sequence simultaneously using a mechanism called self attention. Because the transformer processes everything at once, it has no concept of order. The word dog and God look the same to it. To fix this, we implement a positional encoding class. This injects a unique mathematical signature using sine and cosine waves into the character embedding so the model knows the exact position of a character in the sequence. Inside the transformer model, we use PyTorch transformer encoder. It splits the embedding into multiple heads, learning different contextual relationships in parallel. Crucially, we implement a causal mask because we process everything at once. We have to blindfold the model from seeing the future characters. Otherwise, it will be just cheat and look at the answer. So, how do these models actually learn? So, let's jump into the training part. We use our parse to allow us to dynamically choose whether we want to train the LSTM or the transformer via command line. We define cross entropy loss, which is standard for classification tasks, and Adam optimizer. For every batch of data, we do the following: zero the gradients. We clear the optimizer from the last step. Forward pass, we push our X inputs through a model to get our prediction. Calculate the loss. We compare the prediction to our targets. Backward pass. This computes the gradients. Gradient clapping. Notice the line here. This is crucial for sequence models to prevent gradients from exploding and destroying our model weights. We update the weights at the very end. At the end of the epoch, we save the trained.pth model file and dump the loss history to the .json file. Once trained, we want to generate the text. This happens in the generate. To train the LSTM, we use the following command. So by running this command in the command line, we can train the model using the LSTM. And here is the command line for the transformer training. Once we trained, we want to generate the text. We take a seed text like to be or not to be, and the model and ask the model to predict the next character, append to it text, and feed it back to the model in a loop. A very important concept there is temperature. A temperature of 1 is default. A low temperature, example zero point 0.5, makes the model highly confident, picking only the safest, most likely characters. It becomes coherent but repetitive. A high temperature, for example, like 1.5, flattens the probabilities, giving a chance to unlikely characters. The model becomes highly creative but often misspells the words or descends into chaos. Opening the command line and running this particular command results in generating a text formatted exactly like a Shakespeare play, complete with character names and line breaks, learning all of this character by character. Finally, if we look at our results, we have generated a loss curve using a matplotlib to compare our models. Generally, on tiny data, LSTM uh, converges faster. The transformer architecture is incredibly powerful, but it requires significantly more data and larger dimensional sizes to truly outshine the recurrent architecture. And that's completes the project. We successfully engineered, trained, and evaluated two foundational deep learning architectures from the scratch. Thank you so much for watching.